All right, let's start. Do you have any questions? All right. So last time we were discussing, I think, 2.3, section 2.3. Let me check. Yeah, 2.3. All right. And basically 2.3, right, they give it a name in terms of like the physical phenomenon that the equation tries to model. But here I'll just call it all right, second order linear ODE with constant coefficients. All right, and of course homogeneous. Okay, and the idea is, right, this does model, okay, a physical system, a spring mass system immersed in a viscous, solution. Okay, if A is M, right, B is some kind of gamma, some kind of viscous, like resistance coefficients. And C, right, is going to be K, right, the spring constant. Then that models a spring mass system. But in general, right, there are many models that this equation can cover, so we won't really insist on that, and we just focus on the math. Spring mass system, right, immersed in some viscous solution. All right. Anyway, so mathematically, we were interested in how to achieve the analytical solution. Okay, analytical solution to this equation. You should also keep in mind, right, even though it seems that we take a detour to discussing this kind of equations, it can be, right, and it should be viewed, I mean, at least from the point of this book, as a part, right, of the linear system, sorry, not linear, right, of the system of ODEs, right? You should remember that this has connection, right, to a system, right, of first order ODE, where, right, we say, let's say x1 prime is equal to x2, and x2 prime is equal to 1 over a, right, times minus bx2 minus cx1, okay? Where, so let me write the equation down again, a double prime plus by prime plus cy is equal to 0. So here, right, clearly our x1 is equal to y, and x2 is equal to y prime, okay? So if you make this substitution, you will get to this system, that the system of first order equation that we can also consider. Anyway, right, the point of view that we adopt here is the point of view of the second order linear equation. And we mentioned, right, that the starting point of solving this homogeneous equation is by starting making a guess that the solution is of the form eta lambda t, all right? Lambda can be complex. Complex doesn't mean complicated. Complex really means imaginary numbers, right? Okay, so we list out 3 cases last time. That lambda 1 is not equal to lambda 2, and they're both real, all right? Then the solution is y of t is c1 e to the lambda 1t plus C2 e to the lambda 2t. Maybe let me move back a little bit, right? That with this guess, right, we achieve something called a characteristic equation for lambda, which is you plug in, right? You plug this guess into the equation, all right? And you get a quadratic equation for lambda, which is lambda square, sorry, a lambda square plus b lambda plus c is equal to 0, okay? And from there, right, from there, we observe that we have 3 cases of lambda exactly, right, from the discriminant, right, the sign of the discriminant of this quadratic equation. So case 1 is when the discriminant is positive, then you have 2 real solutions, 2 real roots. Case 2 is when you have repeated roots. All right, then the solution will be C1 e to the lambda t plus C2 t e to the lambda t. Case 3 is when you have 2 complex roots. All right, now, of course, usually, you know, in the normal situation, when you see this equation having a negative discriminant, you say there's no solution, okay? No solution meaning no real solution. But for obvious reason, because of Euler's formula, we do allow the root to be complex here. So in that case, right, the complex root will lead to sine cosine solution. So it's going to be e to at c1 cosine bt plus c2 sine bt. All right. And I want to discuss, right, case 2 and case 3 more in depth today. Right, case 1 we kind of covered last time. So I want to discuss case 2 and case 3. Any question before we continue? All right, so let's look at case 2 first. Case 2, right? When does case 2 happen? Case 2 happen, right, when you have repeated roots. Not at all. No. Case 2 is the case when we have repeated roots, right? And when do we have repeated roots? That means that the characteristic equation, right? Repeated roots means that the characteristic equation must be of this kind of form. Lambda plus, I don't know, let's call it, for lack of letters, right? Let's call it, you know, C1, all right, times square times C2 is equal to 0. Okay, so what I mean is if it's repeated roots, then the characteristic equation is a perfect square. Okay, so pay attention to that. For example, right, for example, consider this equation, y double prime plus 2y prime plus y is equal to 0. Okay, what is the characteristic equation? Lambda square plus 2 lambda plus 1 is equal to 0. You can check, right, by the quadratic formula that this has only solution lambda equals to -1 only, or, right, you can recognize that the above is just lambda plus 1 square is equal to 0. Okay, these two facts are the same. They must imply the other. One must imply the other. All right. So in that sense, right, I said the solution will be C1 e to the minus t plus C2 e to the t e to minus t. Okay. So the first solution is not nothing surprising, all right? Because when you plug this into the ODE, what you get, right, is e to minus t times this. And where lambda equals to -1 is exactly makes this equal to 0. What I want to discuss is the multiplication by t, all right? Multiplication by t is a very common device in ODE, in linear ODE. The rough rule of thumb can be set something like this, which needs to be explained a little bit, but basically whenever you have repetition, okay, and we have seen that in the first order equation where your yp, right, for example, you have seen something like this, we have seen before, where let's say you have the equation y prime plus y is equal to e to the minus t, okay? Then your yh, right, is going to be e to the minus t times c, all right? But if you guess your particular solution to be e to the minus t, that won't work, okay? That won't work. Why? Because exactly that your homogeneous solution is e to the minus t. If you plug e to the minus t in here, you'll get to be 0. So you must guess it to be t e to the minus t with an undetermined constant, right? Undetermined coefficient for you to be able to solve. Something similar is at work here, right? E to the minus t is, a solution to this equation. But if you look for the other, right, you look for the second solution. By the way, right, why do we always expect two solutions in this case? Several reasons. First, right, the order of the equation is 2, all right? So when you integrate twice, you get two unknown, right, two undetermined coefficients as reflected by C1, C2 in here, right? So there are always, right, two undetermined coefficients when you solve second order equation, because implicitly you integrate twice. Or if you want to connect it with the system, you see this is a 2 by 2 system, right? A 2 by 2 system naturally leads to two undetermined two degrees of freedom, all right? So either way, all evidence points to us looking for another solution after we get e to the minus t as one solution. But if you turn to the other root, right, the other root is -1, you cannot make the same guess again, because that will make it back to the same solution. And so your device of going out, of getting something significantly different from that is multiplying by t, okay? So that's the message. Now, I will go in and explore why, right, multiply by t, what's the effect, all right, why multiply by t kind of works here, okay, to show some kind of working behind the scene. But any question on this? So basically, when you get repeated roots, okay, one solution is e to the root, the other solution will be t times e to the root. Okay, so let's take a look, right? So in general, suppose that if we make the guess, right, that y of t is t e to lambda t, right? That's the guess. All right. Again, right, I'm making this analysis based on case 2, meaning that I already know that my characteristic equation is a perfect square, all right? I know that because I have repeated roots. Now, so first, right, I have to plug in the equation. The equation is, right, ay double prime plus by prime plus cy is equal to 0. Also, keep in mind that the characteristic equation is something like this, okay? So if I plug in, right, I have to differentiate this twice. Y prime is equal to e to lambda t plus t, right, lambda e to lambda t. That's y prime. Y double prime, right, will be differentiating this gives you lambda e to lambda t, right? Differentiating this gives you lambda e to lambda t, right? And then plus t lambda square e to lambda t, okay? So after you plug into the equation, right? After you plug into the equation, what do you get? Okay, so you mean in general or in this case? So in this case, right, notice that I'm fudging here. I'm not telling you what C1, C2 is exactly. I'm just saying that it must be a perfect square. That's the only thing that I'm telling you. Why must it be a perfect square? It must be a perfect square because you have repeated roots, right? What does repeated roots means? Repeated roots means that, right, the equation must be factored into the same roots, right? That's what it means to be repeated. And I just throw in a constant outside because, you know, the leading coefficient may not be 1. So that's why. You know, like this. Okay. So actually, right, I think, how do I want to say this? Having said that, right, I think maybe I want to do it with this example first. Okay, maybe this is a little bit too abstract. Let me deal with the example first. So in the example, we got y double prime, right, plus 2y prime plus y is equal to 0, right? The characteristic equation is lambda squared plus 2 lambda plus 1 is equal to 0, which is the same as lambda plus 1 squared is equal to 0. Okay. Now, if I want to analyze the equation, right, that the solution yt is equal to t e to minus lambda e to minus t. Okay. Then y prime is going to be e to minus t e to minus t. Y double prime is going to be e to the minus e to minus t minus e to minus t. Okay. And then plus t e to minus t, which is minus 2 e to minus t plus t e to minus t. All right. Now I will plug y prime, y double prime, and y into the original solution, the original equation. What I'm going to get is, right, that minus 2 e to minus t plus t e to minus t, right? That's y double prime plus 2 e to minus t e to minus t, right? And then plus y, which is t e to minus t. Okay. So what I want you to pay attention to is this, right? When you only have the solution that is e to minus t, that's easy to see the effect. Because when you differentiate, you get exactly this times e to minus t, which is 0, again, right, like I said. But when you have the t term in front of it, you see that the product rule, right, the product rule sometimes differentiate on the t, sometimes differentiate on this. So it kind of breaks it down into two groups. One group is pure exponentials, and the other group is the group with the t in front. Right? These are two separate functions that must perfectly cancel out so that the right-hand side is equal to 0. All right. So my message for you is this, that to understand the effect of multiplying by t to get to a second solution, you want to understand the effect of how, right, the t to minus t group combined and the pure exponential group combined. Okay, so let's see. They combine like what? Notice, right, this minus 2 and this 2 perfectly cancel. So let me just do that. This is e to minus t times 2 minus 2. Okay. What about the t e to minus t terms? The t e to minus t term is, right, 1 minus 2 plus 1 is equal to 0. All right. So what's going on, right? What's going on behind the scene is that, so I may go back to here and show you the abstract result, but what's going on behind the scene is this. You will have e to minus t here, 2, and then you have the effect of lambda minus alpha here. And then the other one, or sorry, let's do alpha minus alpha, all right? And then this, sorry, is e to minus alpha t. And this is the effect of t e to minus alpha t times alpha squared minus 2 alpha plus 1 is equal to 0. Where this is exactly the characteristic equation. Okay. Yeah. So what I'm saying is this, and it's a little bit hard to see. You have to run it through, right, with your own calculation. Basically, there are two groups that operate inside the equation. Okay, when you make the guess to be t times e to lambda t, right? I claim that when you have repeated roots, okay, then the solution will be e to lambda t, which is easy. The t e to lambda t, all right, is what we want to understand why we multiply by t. So multiply by t, right, in terms of the effective calculation is, it will break, right, the solution down to two groups. One with just e to lambda t, right, or e to alpha t as I call it, because alpha is the root. And the other one is with t e to alpha t, okay? And after you differentiate and you combine them into the original equation, you see that basically the t e to lambda t, t e to the alpha t here, right? What it does is, not minus alpha, is that it factors out with the characteristic equation in front. And so by definition, because this is the root, it's going to be equal to 0. On the other hand, right, this one will factor into the linear factor of that characteristic equation. So it always plays out in this way, and that's why I multiply by t. Yeah, okay, I can keep lambda there for you, but what I mean by alpha, right? What I mean by alpha is because the alpha is the, where did I write it? I thought I explained it to you somewhere. Okay. Let me call it lambdas. Sorry. Let me call it lambda. I called alpha because I want to emphasize that's the root, but lambda is fine. So here lambda is equal to -1. Yeah, I should try to be a little more consistent. By lambda, I means the unknown, right? There's no specified lambda. But alpha is the root of that equation, meaning alpha equals to -1. So, but anyway, right? I'm pointing to the structure, so it doesn't really matter. What I'm saying is the structure will always be that the e to lambda t factor multiplied with lambda minus lambda. The t to lambda t factor multiplied with the characteristic equation. And that's why t e to lambda t works, okay? Basically, when you differentiate, if you pay attention, the t to lambda t keeps the same structure as the characteristic equation. And the e to lambda t just pick up the linear fraction from there. That the product rule works down that way. That's all I want to say. Okay. So that is why multiply by t works, as far as as I want to explain in terms of the structure. Now, if you don't want to like get into all of this kind of explanation business, then you can just remember that one solution is e to lambda t, and another solution, right, is t e to lambda t. That's it. When lambda is repeated root. okay? But if you want to understand why, right, the second factor is like this, then you must trace down how, the terms distribute among the equation. And it will distribute into the structure that I'm pointing out. That's what I want to say, okay? Not a big deal, but I think it bugs some people, especially me, to try to understand why, multiply by t works. It works because of this. Any question on this? Okay. So now let's move to case 3. When you have lambda, all right, is the complex root. When lambda is a complex root, then I claim the solution is e to at c1 cosine bt plus c2 sine bt. Good question. Good question. So that comes into some of these things too. So first of all, right, if you really want to seriously analyze this, there are several things behind the scene that you want to address. First of all, you want to show that abstractly, right? You want to show that abstractly lambda e to lambda t and t to lambda t always works when you have a square form. When you have a perfect square form for the characteristic equation. That's kind of what I was trying to point out, when I differentiate, okay? Second, what happens is then you want to say that with a second order equation, you completely covers every solution when you find two independent solutions, okay? When you find two independent solutions, meaning two solutions that are sufficiently different, then because of the linear structure of the ODE, the linear combination of them covers everything. And that, since you ask, if you want to rigorously justify that, you have to appeal to the vector space structure, okay? You have to appeal to the fact that the solution space to this equation is a vector space of 2 dimensions. Therefore, when you find two basis vector, you cover everything. Now again, right, we can lay it all out, discuss into that direction, but that will, take the class into a direction that, right, that's just not conducive to the general public. But yeah, that's the theory behind the scene. Okay, so now I want to address, right, so again, like for the repeated root, I want to address the factor t. Here, I want to address why the I disappears, okay? As someone asked last time, why isn't there an I here, okay? Because naturally you feel, right? So first of all, where do these cosine and sine come from? So the cosine and sine comes from the Euler formula to begin with. The Euler formula says that e to the a plus bi, okay, is cosine a, sorry, what am I saying? It's going to be e to the a cosine b plus sine b plus I sine b, all right, where a, b are real numbers. So first of all, right, when the roots are complex, then following our guess, okay, so first of all, the argument goes like this. First, you solve for the root to be complex. You know what? Let me give you an example first, so make it easy for you to follow. Let's look at, all right, y double prime plus 4y is equal to 0. Okay. So the characteristic equation is lambda squared plus 4 is equal to 0. So the solution is lambda equals to plus minus 2i. Okay. So from here, you immediately conclude that yt is c1 cosine of 2t plus c2 sine of 2t. Okay. And actually, after you figure that out, you see that it's not like earth-shattering to observe that cosine and sine are solutions here. Why? Because, right, if you differentiate cosine twice, you get back to its original form with a negative sign in front. And the 4, right, exactly is 2 square. Right, the 4 is exactly 2 square. So cosine and sine both have that kind of property. So that's why, right, these are solutions. But the connection we want to make, right, is somehow transitioning from the 2i, right, into cosine and sine. So let's go with this example. Basically, right, first of all, the example tells us that the solution will be something like this. Right. If you follow like the structure that okay. So whatever the root is, right? Whatever the root is, you just raise it to e to that power times t. E to that times t. You get the solution. Okay. So now if you trace it with the Euler's formula, right? If you trace it with the Euler's formula, you get something messy like this. You get something messy like C1, right? Cosine of 2t plus I sine of 2t, and then plus C2 cosine of minus 2t plus I sine of minus 2t. Okay. Notice, right, and actually you probably get a suspicion that somehow this can be reducible to this, right? This structure can be reducible to this structure. Okay, and that's exactly the message. These two structures are equivalent. How? How is, first of all, right, it relies on the C1, C2 as the workforce, because C1, C2 here can take any values we want. Okay, C1, C2 are unspecified coefficients. Okay, and exactly like, like actually related to Ron's question, the principle behind, right, the solutions to this second order linear ODEs is you just come up with two solutions that are sufficiently different, then you're good. It doesn't matter what form it takes, okay, as long as they work and they take on, again, they are independent, right? They are sufficiently different. So if there's anything like connected to linear algebra that like Sagar was mentioning at the beginning, is this idea that a vector space is covered, okay, by two basis vectors. Doesn't matter what the choice of two basis vectors is, okay? You can choose two basis vectors as long as they are really basis vectors. Then they cover everything in your vector space, all right? And of course, everyone knows, right, if you want to make your work easy in the future, right down the road, you want to pick a nice set of bases to work with, okay? So here, this is a basis vector. This is a set of basis vectors. But, right, the claim is that this works equally well, but these are nicer in the sense that they are more simple to work with, okay? And by vector here, right, don't think I mean anything fancy like a vector in, multi-dimension. A vector here is just actually a function in time. That's what I mean by a vector in this case. A vector, like a function serving as a vector in a function space, okay? So how to combine, right? Basically the question is how to combine this into this. Exactly, that's it. The key is only that these C's, because we're dipping into complex area, these C's are allowed to be complex. That's it. That's the only secret, right? So you see that, right? If you choose, right? So let me call this form star, right? We choose C1, C2 to be 1 in star. Then you see that, right? Oh, sorry, not 1, right? 1/2 rather. Then y of t, right? y1 of t, which is cosine of 2t, is a solution. And then you choose C1, C2 to be 1 over 2i. No, right? One of them must be minus. So C1 is 1 over 2i. C2 is minus 1 over 2i. Okay? Then y2 of t is sine of 2t is a solution. So in star, meaning I'm picking, right, particular choice of C1, C2 to reduce this complex form into this simple form. Okay? So I choose C1, C2 to be 1/2 in this expression. Then you see this reduced to cosine 2t. If I choose C1 to be 1 over 2i, C2 to be minus 1 over 2i, then this complex form reduced to sine 2t. All right? And so therefore, that's all we have. Y of t is C1 cosine of t plus C2 sine of 2t also expresses all solutions. All right, any question on this? Oh yeah, thank you. Sorry, cosine 2t. Okay, cosine 2t, yeah, thanks. So I mean, let's run through some example real quick, right? And I'm not sure if I can cover everything. I mean, like cases very, very quickly, but for example, let's say y prime, right? 2y double prime plus 5y prime plus 6y, right, equal to 0. And by the way, right, let me just say this too. How would the initial conditions for this kind of problem be posed? The initial conditions, if you care to pose it, will be y of 0 equal to something and y prime of 0 equal to something. Okay, like 1 and 2 or 0 and 1, that kind of thing. And why? Because, right, basically this is a second order, right, system. So it has 2 degrees of freedom, right, C1, C2. So you need 2 initial conditions. And with the view, right, that this is like a mechanical system or something, then what this is saying is you're specifying the initial position and the initial velocity of the system. All right, that's what it does. So with the first order system, right, you only, because that's velocity, you only need the initial condition. But with the second order system, right, you need initial condition and initial velocity if you want to completely specify it. Anyway, right, so this would reduce to 2 lambda square plus 5 lambda plus 6 is equal to 0. I mean 3, all right? I want it to be 3, sorry, to make it easy to factor. Right, so that's going to be, right, 2 lambda square plus 2 lambda plus 3 is equal to 0. So that's lambda plus 3, right, times 2 lambda plus 1 is equal to 0, right? So we got the solution to be C1 e to minus 3t plus C2 e to minus 1/2 t is equal to 0. Oh, sorry, not equal to 0. Is that. And if you want to solve for C1, C2, right, you plug in y of 0, right, which is C1 plus C2, which must be 1. And then y prime of 0, which is minus 3c1 minus 1/2 c2, must be equal to 2. And then you solve for it, okay? And all the other cases are similar. Oh, did I do it wrong? 2 lambda, hold on. So 2 lambda, oh, sorry. There's a 3 lambda here, right? Yeah, thanks. 3 times lambda plus 1. So 2 lambda times lambda plus 1 times plus 3 times lambda plus 1. Yeah, thanks. So it's going to be 2 lambda plus 3. And then you got lambda plus 1, 3. No. So I got minus t minus 3/2, right? So this is still true, but the second one would be minus c1 minus 3/2 c2. Yeah. Does this work now? This should be correct, right? All good? All right. So that's all I want to say, right, about second linear, uh, second order linear ODE with constant coefficients, homogeneous. Let's move on to 2.4. Actually, maybe let me say something like this real quick. This method, all right, this approach also works for higher order linear ODEs with constant coefficients. Okay, what does that mean? Let's suppose you have a really high order equation, right? And I'm just going to make things up. Let's say y to a fifth plus 3y to a fourth minus 4y cubed plus 10y squared minus, what am I saying? Y to the fifth order, fourth order, third order, and then let's say 15y prime plus 20y is equal to 0. Okay, suppose you have that. Then exactly the same way, by guessing, okay, y of t to be eta lambda t, you can go to the characteristic equation that says 4 lambda to the fifth plus 3 lambda to the fourth minus 4 lambda cubed plus 10 lambda squared minus 15 lambda plus 20 is equal to 0. Okay. So the game there, though, is whether or not you can solve for lambda here, right? There'll be 5 values of lambda. And of course, right, I'm not claiming I know how to solve this equation at all. But in theory, if you can somehow obtain the roots of this equation, then, right, the solution will be just C1 e to the lambda 1t plus C2 e to the lambda 2t all the way to C5 e to the lambda 5t. With the caveat, right, that if you have complex solution somewhere, then the complex solution will happen in pair. So those pair will get the treatment of cosine and sine, as we did, as we showed in the second, in the case before. If you have repeated roots, then you multiply by t, and then you multiply by t squared, etc. Until you get out of the repetition. So in general, right, whatever we said from before applies to higher order equation. You won't see them too much for several reasons. First of all, right, no one bothers to know how to solve this equation. And second, with higher order system, with higher order equation, then the system of linear equations starts to be more efficient. I think at only a second order, like the case I'm telling you here, that this approach is faster than when you look at the system. But with higher order, the system starts to be more efficient because you can deal with eigenvalues, eigenvectors, and not with, solving a fifth order equation. But in theory, all right, this works as long as you know how to solve this. But that's all I want to say. Okay. So let's go to 2.4. Some special case where we can solve the system of ODEs analytically. Okay. So the theme of the presentation seems like this, right? 2.1, 2.2 are qualitative approach. 2.3, 2.4 talks about analytical solution. But of course, under very special cases, all right? Analytical solutions always suffer from that kind of, drawback, that you must make special assumptions so you can do some special calculation, right? 2.3 assume that we'll have a second order linear system, a linear equation to work with. 2.4, as you see, doesn't do anything earth-shattering. It's just pointing out some really obvious case that if you pay attention, you already have it anyway, okay? So first of all, so 2.4 talks about two special cases. The first case is when the system is completely separable. I don't know why they bother to mention this. But what they mean is you have dy1 over dy dt, right? dy2 over dt. And basically the top equation only depends on y1. The second equation only depends on y2. I mean, yeah, you can couple them and you can call them a system, but I don't think anyone bothered to call this system. These are just two different equations, okay? So forget that. But they do mention it, so I want to mention it. The second case is a little bit less trivial. And I want to call this the triangular system. In the sense of a triangular matrix, okay? Upper and lower triangular matrix that you have seen in linear algebra. Triangular system goes like this. Basically, this is going to be, it can be upper or lower, doesn't matter. If this is like, let's say this is lower, okay? Lower triangular. And what happens is you start to populate more dependency as you go down. let's say call this F1, okay? F2 ty1, y2, dy3, F3 ty1, y2, y3, etc. Okay. So first of all, do you understand what's going on in this system? And second, do you know how to solve it? I mean, at least in theory, right? Not that you be able to solve it in all cases, but what is the meaning of this system and how you solve it? Yeah, exactly. It's just exactly what we call substitution. Yeah, we solve by substitution, right? So obviously, I don't imply that you can even solve the first one to begin with. But you see, the first one is not a system, right? The first one is just an equation by itself. So it's susceptible to a first order, right, solution, whatever the method it is. But after you solve it, then it becomes known. Then you plug into a second equation. If you plug into a second equation, then the second equation, you know, reduced to a single equation, right? It's no longer a system because now y2 only depends on y2. So if you plug that in, then you can look at this as a single equation. And then, right, after you solve for y2, you plug y1, y2 into this, right? So that's exactly substitution. It's something like this comes to mind. Let's say y1 equals to 1, y2 equals to, y1 times y2, y3 is equal to y1 plus y2 divided by y3, that kind of thing, right, etc. Right. You can exactly, right, you know what y1 is, you solve for y2, and then from there you go all the way down. Of course, I'm not writing ODE, I'm writing equations, but right, the ODEs exactly operate in the same principle. Any question here? So of course, I might be writing something nonsense here, right? But is it okay? So let me explain why I call this lower, right? Lower because I think it populates like this. The system gets more and more, right? More and more, start with y1, right? And then y1, y2, like that, right? So it's lower triangular. You could, again, right, it's completely decorative, but you can start out with something like yn only depends on yn, right? And then you start with yn minus 1, depending on, right, yn minus 1, yn, all the way, right, up to y1, right, sorry, prime, right? y1 prime only depends on everything, right? And so you solve it, right, from the bottom up, right? I guess we wouldn't even bother with that. But if you look at the shape of the dependency, right, it looks like this. So I call it upper, but, Okay, any question? So let's look at some example, right? I have here, I think problem 5 in the book, 2.4, problem 5, where they look at, right, dx dt is 2x plus y, and dy dt is minus y. Okay. Now, it's admittedly a system, right? But I think everyone knows how to solve this, right? First of all, we obviously solve for y, right? So clearly y of t is, let me call C2, okay? Eta minus t. Agree? Then we plug in, right? We got dx dt is 2x plus c2 e to minus t, right? So then now you see that this equation, right, is susceptible to the treatment of whatever you want, right? Integrating factor or, homogeneous, with the particular solution approach. What I want to remind you, right, is that C2 is like a free, right, is a free constant down here. But in this equation, it's not a free constant, all right? It's a fixed constant because you already chose it when you solve for y2. So in other words, right, C2 here has to be kept fixed, okay? I mean, of course, from the point of view of the system, it's still a free constant. But from the point of view of this single equation, right, it's a fixed constant, given from the outside, right, given from the solution to y2. So in other words, right, let's just solve it. Here you got x prime minus 2x is c2 e to minus t, right? So the homogeneous solution, right, is e to 2t, right, c1. Yes. And then you guess, right, yp of t, sorry, not y, right, x1, xp of t, right, is a constant e to minus t, right? And then you plug in, you got a, right, e to minus a e to minus t minus 2, right, a e to minus t is c2 e to minus t. In other words, you got minus 3a is equal to c2, or a is minus 1/3 c2. There is no 2t. They are function of t, right? So the solution is c1 e to 2t. Am I wrong? Did I make a mistake? Okay, so basically then, right, this is what I mean by C2, right, is treated as exogenously given, okay, in terms of the equation given by x, given in x, all right? So in other words, right, you solve for the undetermined coefficient in terms of C2. So in other words, right, the solution will be something like x of t will be C1, right, e to 2t minus 1/3 e to minus t, 1/3 C2. Error in XH, you mean here? Does anyone see what Saga was saying? I'm not following. Anyone else see something? No, right? If you look at x prime minus 2x equal to 0, right? If I look at e to 2t, right? Prime is 2 e to 2t. So e to 2t prime, right? Minus 2 e to 2t is equal to 0. I'm really at a loss. You claim I make a mistake here. Yeah, no, I think it's good. I think I think you're making a mistake, Sagar. Yeah, it's eta 2t. All right. Yeah. Yeah, I don't know. I mean, I have to pause because sometimes I can make a arithmetic mistake, like you saw with the factorization. So I want to kind of double check on my work. But okay, so right, this is fine. So yt, right, is going to be C2 eta minus t. All right. So that's a solution to a system. Okay, explicitly, analytically. Okay. Now, any question here? So this is the solution to this, right? The book called partially decoupled, but I call it, you know, triangular, whatever. Now, I want to kind of, so this is fine, right, at this level. But notice how, right, x depends on two undetermined coefficients. Okay, x depends on two undetermined coefficients. That's not surprising because again, right, x here is not an equation by itself, right? X is a part of the system. The reason why y only depends on one unknown coefficient or one undetermined coefficient is because, right, y is the equation standing by itself. Okay, but in general, right, when you solve a system, you expect C1, C2 to appear in both solutions. So a sneak preview, but here is a way that we will write the solution in the future. It will be this C1 10 eta 2t plus C2 minus 1/3 and 1 eta minus t. All right. Now, this is the linear algebra language that we'll be using. Okay. And also a sneak preview, the previous system, right? This system will be written as xy, right? D over dt is equal to 2, 1, 0, minus 1 xy. Okay. Which is, again, right, you can check that is this. And d over dt, right, applied to a vector means you just differentiate each coordinate. And finally, right, I will say this. We'll work on this. We'll talk about this. But the relation between this, and this, right, it has an intimate connection. 1, 0, right, and 2, and then minus 1 and minus 1/3, 1, are the eigenpairs of the matrix 2, 1, 0, minus 1. Okay. Yeah, I mean, it's like this, Shiv. I mean, basically, if you ever have something like ax plus by cx plus dy as a vector, right? This is a 2x1 vector. It can always be expressed as a b c d times xy, which is a, right, 2x2 times a 2x1. Yeah. Okay. So yeah, so just one more thing, right? In case those of you who don't quite recall what eigenpairs means, the single here is eigenvalue. The scalar is the eigenvalue. This is the eigenvector corresponding to that eigenvalue. So if lambda, right, and v is an eigenpair of a matrix A, right? A must be a square matrix, all right, n by n. You don't have eigenvalue, eigenvector for non-square matrix. That means A times V is equal to lambda times V. Of course, we require that V not to be the zero vector. Otherwise, right, this always works. This always works for any trivial lambda. So, right, so let's show you that this works, okay? Again, I'm not teaching you, I'm not showing you how to find these things or anything. I'm just pointing out the connection between this system, all right, of differential equations with the linear algebra structure behind it. Okay, we'll discuss this more systematically when we go to chapter 3. But anyway, right, let's see. 2, 1, 0, minus 1, okay, as a matrix, right, times 1, 0 will be what? Is 2, 0, right? Oh, so what I mean is a matrix A is a matrix, and the subscript just kind of say it's size n by n. It's not an xn. A with size n by n, where the n by n here is just basically redundant, because I just want to emphasize that you must have a square matrix to have eigenvalue, eigenvector. You don't have that concept for, you know, rectangular matrix. Yeah, that's all. Okay, and you see this is 2 times 1, 0, which is exactly the value 2 here. Okay, and then you have 2, 1, 0, minus 1 times minus 1/3 and 1 will be what? Minus 4/3 plus 1 is 2/3, right? And then that's going to be minus 1, right? Wait, no, what am I saying? I can't even multiply. Sorry. Yeah, minus 2/3 plus 1 is 1/3. Right. Yeah, I'll do that. 1 second, Lauren. Albors, what are you correcting me on? Which is minus 1 times minus 1/3 and 1. No, not minus 1/3. The second one is this and this, which is minus 1. Yeah. Okay, sure, might as well. So matrix multiplication. All right, so matrix multiplication is done with a, let's say, n by m and m by, let's say, p, all right? So basically, this is n rows, m columns, m rows, p columns, all right? It's important that this and this match, all right? If it doesn't match, you can't multiply. And so you have A, right? Basically A with n rows, right? M columns, and B, right? So this is A, and B with, you know, M rows, right? So, okay. And then P columns. And so what happens is actually for the A, you should look at as row, okay? And for B, you should look at as columns. So rows, column, okay? And if you look at it as a rows, then this is a row with size M, because exactly you have M columns, okay? Like this, right? Rows with size 2, row with size 2. Here you should look at as column of size M. So that's exactly why the M must match, because then you just multiply row with column, right? And you put it corresponding to the position. So, you know, the product, right, the AP position, let's say ij, will be row I of A dot product with column J of B. Okay, so that's why rows of A and columns of B must match in dimension. So you see, right, this times this is 2 times 1 plus 1 times 0 is 2. This times this is 0 times 1 minus 1 times 0 is 0. All right, this times this is minus 2/3 plus 1/3 is 1/3. This times this is minus 1. Okay. Yeah. There is another point of view of a matrix multiplication, which I'll talk about, when the time comes. But you should also try to remember this point of view, that if you have A times X, let's say A, right, is M by N, and X is N by 1, then this will be the sum of Xi, and then times column I of A, like this. I runs from 1 to N. So in other words, a matrix times a vector should be viewed as a linear combination of columns of A. This point of view is consistent with this point of view, but in linear algebra, this point of view is used much more common. All right, when the time comes, I'll emphasize that more. But for now, if you just want to kind of mechanically calculate out what the thing is, you just do rows, column, that kind of stuff. But again, right, I mean, this is a preview. We'll get to chapter 3 soon, but we do this, on a daily basis. For now, right, what I want to say is, maybe you already forgot, is this is the system that is triangular. So the point of view is we pick up from the equation, solve it, plug that back into the previous one, reduce that down to an equation, solve it again, and then we get it, okay? Any question? All right. So for the last 7 minutes or so, I'll do 2.5, believe it or not, because it's simple. It's Euler method. Okay. And this is really your old friend. There's nothing there really. So for the Euler method, right, we will take the point of view that we got a vector y. We look at d over dt, right? The derivative will be a function, a vector function of t and y. We're given the initial condition. Okay. So pay attention, right? This is 0 as a 0 in time, right? This is a 0 in time. And of course, right, the initial condition should be a vector, all right? A vector of whatever size that the system is. And we want to approximate let's say y of big T, all right, for some given t. Let's say t equals to 1, right, is a standard choice. Of course, we're also given the step size, right, delta t, right, 0.25, that kind of thing. You are used to it by now, right? What do? Same old stuff, really. Y vector k plus 1 is approximately y vector k plus f of tk yk times delta t. Same thing, okay, same thing. Of course, right, except that it's in the vector form. It's in the vector form, that's all. But Otherwise, right, it's exactly the Euler scheme that you have worked with before. Now, why does this work? Why it works is, like just for example, if you look at a system like this, right, just as a demonstration, what it says is at heart, right, this is still the derivative of x. So if you use the Euler method on x, all you need is the approximate value of y at that point, and you can step to the next step. So same thing here. Suppose you have an x here, who cares? Then all you need, right, to step to the next step of y is the previous value of x and y. But you have it because at each step, right, you walk to the next vector. So, right, the concept here is nothing more miraculous than the good old Euler method. If you want a more geometrical interpretation, right, is exactly what you do with the solution curve. Here, I'll just do a 2-dimension, right? But let's say here is y2 and here's y1, right? You start out with the vector of the initial condition. This is y at time 0, right? Well, this is where the vector field starts to give you a meaning, right? The vector field, right, at this point will point to exactly, right? The vector field here, right, is exactly, f, right, at 0, y0, right? And then you follow this, right? That's what you say. That's what they say, right? Follow this with the delta t size. If you follow this with delta t size, then you get to the next point, which is maybe y at 0.25. And then at that step, you calculate the vector again, follow it, follow it, follow it, right? So that's exactly, the mathematical writing of tracing out the solution curve. I'm not sure what you mean by the system, Daniel, right? The solution, or basically here, x and y, right? This is the vector. But when I say, when I say the system, right, I have something very specific in mind. This whole thing is a system, right? Obviously, it's not a vector, right? But the vector is the solution inside the system, yeah. Okay. Yeah. So I don't know, right? I guess let's just do some layout for you, but you already see what's going on, right? Let me see here. So for example, right? I think the book gives something like x prime is y prime is minus x plus 1 minus x squared times y. Okay. And they say that xy at 0 equals to 1, 1. Okay. And they want to do some approximation with step size 0.25. Okay. So guess what, right? Your table is very much the same as the other table with enlarged, right, value. So if you want, right, you can do t, x, right, x sub k, y sub k as 2 separate columns, right, and then f of, t, x, k, y, k like that, right? I think I prefer maybe to keep them as a vector, who knows? But so for example, right, this is 0, right, and then 1, and then 1, right? And this will be a vector, right? So it will be 1 minus 1. Okay. Now I think, so, and then you move on, right? You moved on to 0.25. Okay. And then this will be 1.25. And then 0.75. Okay, you see why? Because you let 1 plus 1 times 0.25, right? That's delta t is 1.25. 1, right, plus minus 1 times 0.25 is 0.75. And then, of course, right, you plug this guy into this to get the second vector. And then you continue, right? And then 0.5, so on and so forth. If you want, Sagar, anytime you touch vector, you might say you use linear algebra. I don't see much here. You know, you're just adding vectors, really. All right. So I just want to say this, right? It's up to you on how you want to organize this. For me, I prefer to organize like this. Right. So I would do 0, vector 1, 1, vector 1 minus 1, 0.25, vector 1.25, 0.75, right, etc. A little algebra. Yeah, sure. Arithmetic, you mean adding things, right? But the book, right? The book, like they try to do this. T, X, K, Y, K, and they call something like MK and NK, all right? So they really keep 4 separate variables, where of course this is 0, this is 1, this is 1. This is the first coordinate of the F. So it's gonna be what? 1, and this is going to be minus 1. Right, and then they do 0.25 and they do 1.25, 0.75, you know, first coordinate, second coordinate of F, right? Your call, right? However you want to do it, I don't care. I prefer to think of it as a vector, but I can understand, right? Sometimes making it long is a little bit more cumbersome, but that's that, okay? At the heart of it is exactly just the old good old order. Yeah, the solution, right? There you go. Notice I wrote this. To approximate vector y at t. You see? Right? Yes. Of course, someone can be tricky and say, you know what? I want to approximate in this equation. I want to approximate, let's say, x of 1. But guess what? Because x is inside a system, right? Okay, you're interested in only x of 1. But absolutely, right, you get y of 1 for free. There's no way that you just get a single x of 1 by tracing out the x only, right? You get the y by default. So might as well present both. But I know someone can just be interested in x. You mean like this? Yeah. So that's why I say, right? I prefer this. But I was like, I guess I was doing a hybrid approach here. But yeah, like for the table, I prefer to keep everything as a vector. But again, right, I'm not against folks keeping things out, you know, separately. It's up to you. I just want to point out that conceptually we are looking at this as a single point. So I feel like keeping that as a single point helps, but it's up to you. All right, so I think I'll call it a day. I'll see you next week. If you have any question, I'll try to address. If not, I'll see you. Yeah, thank you. You too. Yeah, you too. Yeah, it will. It will. I'll write down the homework soon. You too.